All right, welcome to Notes 7-2, Day 2, Graphs of Inverse Functions. So before we start, they've already graphed this for us, and so I'm going to use the graph over here to regraph it. And the reason is a lot of us have forgotten how to graph a quadratic, and so I'm going to do that for you. All right, so to start with, we're going to graph our parent, and the parent is always y equals x squared for a quadratic. And so those values would be -2, -1, 0, 1, and 2. And when I substitute those in, when I square -2, I get 4. When I square -1, I'll get 1. When I square 0, I get 0. And then 1 and 4. And that's my parent. So I'll start off with 0, 0, 1, sorry, -1, 1, +1, 1, and then -2, 1, 2, 3, 4. And +2, 4. And there's my parent function. Now I'm not going to sketch it in, I'm just going to sketch these 5 points. Next, we have to recall what each of these values do. So this is called vertex form. And in vertex form, if A is negative, the graph will reflect across the x-axis like such. If A is positive, it will not. If A is a value between 0 and 1, meaning like 1/2 or 3/4, then what will happen is all of these y values will be multiplied by that. So for example, if A were 1/2, this point would be half as high, which would be 2. This would be 1/2, this would still be 0, this would be 1/2, and this would be 2. And so our graph would get compressed down, or vertically compressed. And if A is a value larger than 1, say for example 2, all of these values would be doubled. And so those would be like 8, and then 2, and then 0, and then 2, 8. And so this graph would be vertically stretched or narrower. All right, H is going to shift your graph left or right. It's always the opposite of the sign. And so for example, if H is +2, this graph will move to the left 2, and it has. And if H is -2, it will shift to the right 2. And then finally, K will shift your graph up or down. So in this case, A has not changed. A is 1. So no scaling, no reflecting. H has shifted the graph to the left 2. So what I would do is I would shift each of these points left 2. And K was 0, so it has not moved up or down at all. And this would be the graph of this function. Now, they said that they wanted us to graph the inverse function. So remember from yesterday, one way to do that is just to count diagonally. And so that's what I'm going to do. I'll start off with the vertex. I'm 1 unit diagonally away, so my new vertex will be there. This point is 1, 2 units away, so I'll be 1, 2 units diagonally. This point is 1, 2 units, 1 and then 1 more. And then this point is 1, 2, 3, 4 units, so 1, 2, 3, 4 units. And then finally this point is 1, 2 units, so 1, 2 units. It'll be right here. And here's my inverse function. Right, I missed that point, but okay, so they've graphed it for us. It says first we'll graph our original, which we did. Then we'll graph this line y equals x, which we did. Then we'll sketch the inverse function. And it says, is the resulting curve from the reflection a function? Explain why or why not. So is the resulting curve from the reflection a function? So in order to be a function, it must pass the vertical line test. So our original graph will pass the vertical line test. Anywhere on this graph that I draw a line, a vertical line, I will only cross through the graph in one spot. However, on my inverse function, I will cross in 2 spots, and so this is not a function because it fails the vertical line test. Okay, so the next question is, what domain could you use on f of x, that means our original, so that both the original function and its inverse are functions. Is there more than one possible domain that would generate an inverse function? Explain your reasoning. Okay, so the domain that we could use on the original function is, well, let's take a look at if we were to solve this algebraically, what would we get? Okay. All right, so if I were to look at my domain of my inverse function, so my function is f of x equals x plus 2 quantity squared, and I wanted to find algebraically my inverse function, I would rewrite f of x as y, I would switch x with y and solve for y. I would get square root x equals y plus 2, subtract 2 from both sides, square root x minus 2 is equal to y. Excuse me. And so my inverse function, f inverse of x, is square root x and then minus 2. And so I know that the domain of this function is that whatever's under the radical cannot be negative, so x has to be greater than or equal to 0. And I know that the range of this function is, I'll go back to this point, right? I'm going to solve for y, so I have y, I'll add 2 to both sides, plus 2, and y plus 2 has to be greater than or equal to 0. Therefore, y must be greater than or equal to negative 2. So here's my domain and my range of my inverse function. So the domain and the range of the original function is that my range will become my domain. So that's x greater than or equal to negative 2. And my domain will become my range. So y greater than or equal to 0. So algebraically, there's my domain. And if I look graphically, my domain, right, is from x is greater than or equal to negative 2. And so only on the right-hand side of my graph. So yes, if x is greater than or equal to negative 2, the inverse will be a function. Similarly, right, because then when we reflect it, we would only get this portion of the graph. Right? Similarly, though, if we had the opposite branch, this side of the graph, we would only end up with this part of the graph as an inverse. So yes, there is more than one. If x were less than or equal to negative 2, we would also have a function. Okay, so it says, but generally we don't take the bottom half, right, the negative case of our radical, which is this case. This is the positive root, and this is the negative square root. And so we would use this boundary. All right, the graph of f of x, graph f of x, the line y equals x, and f of inverse of x on the coordinate plane. Use the restriction of the domain x is greater than negative 2. And so that's what they've done. They've only graphed this portion, which is what I did right here, right? I'm not sure why they're telling us to graph it if they're graphing it for us. However, if you were to replicate this, I hope you would be able to do that. So let's go ahead and flip it over to the back side. And it says, check your understanding. What is the relationship between x and y intercepts of a function and the x and y intercepts of its inverse? Explain your reasoning. All right, let's go back over here and if we can see a relationship. Okay, so the x-intercept over here was negative 2, 0. And the y-intercept was 0, 4. And that was for our original function. On our inverse function, our x-intercept is at 4, 0, and our y-intercept is at 0, negative 2. right here. So do you see a relationship between these? I see a relationship. The relationship that I see is that the x-intercept is related to the y-intercept. They're the same numbers, but the x and y values switch. And similarly, the y-intercept is related to the x-intercept, but the x and y values have switched. So my relationship for number 12 is that the x-intercept of f of x is the y-intercept of f inverse x, except the x and y values switch. This is also true for the y-intercept. Okay, it says graph each function, the line y equals x and its inverse on the same coordinate plane. Determine the domain and range of each so that both f and f inverse are functions. All right, I'm going to come over here to do the first one, x squared plus 3. So f of x equals x squared plus 3. All right, so my a value is 1, so there's no scaling, no reflecting. And then this is my k value, so this is going to shift up 3 units. So I'll graph my parent function, which is always the same location. It's 0, 0, negative 1, 1, negative 2, 4, 1, 2, 3, 4, and 1, 1, 2, 4. And now I'm going to shift this graph up 3. So I'll shift every point up 3, 1, 2, 3, about right there. 1, 2, 3, 1, 2, 3, 3, and about right here, 1, 2, 3. So here is my f of x function. Now I'm going to graph the line y equals x, and I'm going to reflect it across this line to find my inverse function. So that would be 1.5 units, that's a half, and then 1. This would be 1, 2.5 units, so a half, 1, 2. This is 1.5 units, so 1, or a half, and then 1. This point is 1, 2, 3, 4.5, so a half, 1, 2, 3, and 4. And finally, this point is 1, 2.5, so a half, 1, and 2. And here is my inverse function. Now, it did say, however, to determine the domain and range of f and f inverse so that they're both functions. So when I graph this, they're no longer functions. So when I graph this, I would only want to graph this portion of my graph, and I'd only want to graph this portion of my graph. So this will be ignored, and this will be ignored. And the value for which that's true is x has to be greater than 0. Do we see that x is larger than 0? If x is larger than 0, greater than or equal to 0, we will only get this side of the graph if this is the side of the graph is where x is less than 0. And so this is my restriction on the domain. X has to be greater than or equal to 0. And that's the domain. And then the range, I don't see, I would have to, for me to do this, I would say for the range, y has to be greater than or equal to 1, 2, 3. So y has to be greater than or equal to 3 would be the restriction on the range. And then we can see that that's true, that x is greater than or equal to 3 and y is greater than or equal to 0. And so our domain and range has switched. Okay, let's do one more, this final one. So let's graph our original. And this time I'll be careful not to graph that second branch of my equation. So my parent, this is going to shift right 1 and up 2, and there's no scaling or reflecting. So I'll graph the parent 0, 0, 1, negative 1, 1, 1, 1, negative 2, 1, 2, 3, 4, and 2, 4. And I will shift this graph right 1 up 2. So right 1 up 2, right 1 up 2, right 1 up 2. And remember, we would have the other branch as well, but since the function, the inverse function, will not exist, this half of the graph won't exist, we'll only graph this side of the function. You can see there's the other side over here, but we're not graphing it. All right, we're going to reflect it across the line y equals x. So I'm going to count crosswise 1 and a half, 1, a half, and then a half, and then a half, And here is my inverse function. You could see that this would have not been a function if I had graphed the second branch. And so the values of the domain and range of the original. So on the orange, x has to be greater than or equal to positive 1. Y has to be greater than or equal to positive 2. And you can verify that algebraically. I am going to do that actually. I'm going to verify it algebraically. So our original function f of x equals x minus 1 squared plus 2. So I'm going to just algebraically solve for the inverse. So I'll switch x with y, and then I will solve for y. So I'd subtract 2, x minus 2, and then y minus 1 squared, square root both sides. I get square root x minus 2 equals y minus 1. I would add 1 to both sides, and I get y equals the square root of x minus 2 and then plus 1. And so if I were to find the domain and range of this, I know that whatever's under the radical has to be larger than 0. So x minus 2 has to be greater than or equal to 0, which tells me x has to be greater than or equal to 2. Now look at, there's my domain of my inverse, there's my range of my original. And then also I know that going back to this step right here, I'm going to use this line where the radical is already isolated. So I know y minus 1 has to be greater than or equal to 0. So y has to be greater than or equal to 1. And there we go. There's my domain. Sorry, my domain of my original is the range of the inverse. So we verified that algebraically as well. All right, guys, I hope you had a good, or that you took good notes. And I will see you in class tomorrow.